Our next speaker for this session is Mr. Gary Lyles. Mr. Lyles has a degree in mechanical engineering, and he's been with NASA since 1976 in various roles. He's been the chief engineer of the Space Shuttle main engine of the Space Transportation Systems Chief Engineering Office. He's been the chief of the Canoga Park Resident Office for the SSME Project Office, division chief for the Propulsion System Division of the Propulsion Laboratory, and now he's a member of the Senior Executive Service and manager of the Advanced Space Transportation Program at the Marshall Space Flight Center. His team is responsible for developing NASA's space transportation and propulsion plans for developing NASA's for the next 25 years. And the team has completed a draft, and Mr. Lyles is going to address that with you today.
Well, thank you. Didn't realize when I came that I'd be following Scott Carter. I appreciate the audience, but I know why you're here. Have a hard time standing behind microphones. I'll try to speak up if I run away from it, which I normally do. But I get excited about talking about this program. As you can hear from my resume, I worked in engineering my whole career. I left the chief engineer's job here assisting me to be a program manager. Never been or thought about being a program manager before, and which is probably all right, because I'm not sure there's ever been at least a transportation program, technology program like we're putting together here. The program's relatively new. We started the planning in late 1995, completed in early 1996. So we're in the process of ramping up, of convincing our Congress and our President that we are a viable program and should be funded. I'm going to give you a picture of the initial plans that we put together in early '96 and show you where we're heading after some replanning in '97. So I'll flip charts. Again, I'll try to speak up. If you can't hear, tell me. I'll run back behind the microphone. We got an administrator. Try doing this. Got an administrator that is refocusing NASA on our roots in many ways. He feels like, and is convincing the rest of us, that what NASA's job is, and he has succinctly put it as our job is innovation and inspiration. Our job is to inspire industry to do great things, and we are testing that in some of our new programs, including the X-33, which Gary Payton will talk about later on, I think tomorrow maybe, or later on this afternoon. Dan Dunbacher is here, who's also working the X-33 program. But we have initiated some critical technology efforts. And they're all geared with reducing the cost of space. NASA wants to go to Mars. In 1992, we did a study of going to Mars, and the price tag that came out of that study was $450 billion. Scott Carpenter was talking about the amount of money that we've been able to spend in the space program. Well, the country choked on $450 billion. As long as we have a price tag associated with going to Mars like that, we're not going to go to Mars. So our total objective is getting the price of spaceflight down. The Marshall Space Flight Center in Huntsville, in which I work, has been assigned 3 lead center responsibilities by the new enterprise of aeronautics and space transportation technology within NASA. Those 3 are the Advanced Space Transportation Program, which is the core technology program that supports all the transportation needs of the agency. The X-34 program, which will fly in early '99, that's a small flight demonstrator. And the X-33 program, which will demonstrate the technology that will allow us to go single stage to orbit. The X-33 will also fly in 1999, and many of you have seen the Lockheed Martin concept, lifting body concept, for doing that. The agency is kind of being rotated 90 degrees on how we've operated in the past. This is an important chart. Very subtle, but very important. And the reason is, in the past, we have generated objectives, things we want to do in space, and out of that, we have generated mission requirements. Out of those mission requirements, we have put together technology programs to enable those missions. Very top down. And the future is going to look like this. NASA is going back to working technology. And we are going to generate objectives within the enterprises of NASA. And out of those, we're going to generate the technology program that will allow us to go implement those. And as the technology matures, out of that will come the missions that will allow us to go do the things that we want to do in space. We're trying to avoid this chart in the future. If you plot earlier than 60s, the price is even higher than that. It's an amazing chart, really. But this was our expenditures during the Saturn program. This is just development expenditures. Our expenditures in the development program of the shuttle. Those are high because we did all of our technology and development work within that program. And when you create the mission and go do the development work there, it's a very expensive proposition. The other significant thing about this chart is once you've done it, spending goes to zero. The technology dies, and you don't have a technology program again until you have another mission to do. And so we didn't have a technology program between Saturn and Shuttle, really. And we had to create the technology needed for the space shuttle. For example, the material in the turbine blades of the space shuttle main engine was not characterized. Excuse me. When we went into development on the space shuttle main engine, we had to do that materials characterization within the development program of the space shuttle main engine. In the 80s, we did very little in the way of technology. We did a lot of studies as part of the ALS, Advanced Launch System, National Launch System, NLS. We couldn't figure out what to call NLS. It's sometimes a new launch system, sometimes a national launch system. There was some focused technology work during this time, but it basically died off to nothing because the cost of developing that system was too high. We're in a program now with the RLV, Reusable Launch Vehicle, ASTP, where we're going to try to mature the technology to the point where these peaks will be much, much lower, and the country can afford to go to places like Mars. You heard Mrs. Johnson-Fries this morning talking about the commercial value of space and getting the market involved in going to space and that not being a political type thing. NASA believes in that. NASA intends to work within this box, which is basically maturing technology up from the base research and concept definition up through system level technology. But especially in Earth to orbit, once we get to this point, We feel like that it's our job to retire the risk, the technology risk of developing the next spacecraft to the point where industry can go off and develop that launch vehicle. And the reason they can do that is because we've lowered the risk and there's a market out there for it. We're testing that concept now with the X-33 and RLV program, where industry is putting up significant funding in the flight demonstration of the X-33 program with the desire to make that an operational space launch capability, a commercial space launch capability. Business analysis says there's a market big enough out there to be able to go do that. Of course, NASA is going to stay in the business of development and certification for flight and massive unique things. We don't expect the industry to go out there today and explore Mars. We will probably have to go do that. So a significant amount of funding will go into those kinds of things. But where the market's there, we expect the industry to be involved. The planning process has looked a lot like this, and if you think that looks a lot like the Deming cycle, that's exactly what it is. We thoroughly believe in the closed cycle planning process. We've gone through basically looking at the external environment. What is the needs out there? What does the DoD, what does commercial want to do in space? What does NASA missions look like? Our science community, what do they want to do in space? And what kind of transportation systems do they need? We've analyzed that and basically built the program from the market top down. We then go through a concept selection process, and there's an unbelievable number of new ideas out there. And old ideas which never came to fruition, but we're getting to the point now where the technology is becoming available to do that. And you're in an advanced concept session, and I intend to show you some of that as we go through there. But there are ideas out there that we believe will bring the cost down of access to space. We have formed partnerships with the other NASA centers, with DoD, with the industry, and we're using that technology community to generate these concepts and the technology needs required to go to lower the cost of space transportation. We then go implement the program. We're very product-oriented. And product-oriented means not generating paper. We're demonstrating technology where we can on the ground, and where you can't demonstrate the technology on the ground, we intend to fly it. There are some cases where we believe we have to fly the technology to be able to lower the risk to the point where it's a viable solution. And we can't do it without the peer review, which will keep us on track. A little bit more detailed look at the planning process that we've gone through and continually are going through. It looks like this. Again, we built the strategy top downs and bottoms up, starting with the needs of the country, looking at the challenges, and we have now, I think, the best strategic plan that NASA has ever put forward. It's a forward-looking plan that looks into the next 25 years. It gives us guidelines of what we ought to be doing as a NASA. And out of that comes what we ought to be doing in the space transportation area. One thing that we want to do is explore Mars. Commercially, communications, for example, is a big business. Pharmaceuticals look like a next booming business for space. There's all kinds of commercial uses for space out there. And of course, the military is looking at things like the military space plane, which we only look at from a synergy in the technology, basic technology area, with the things that the DoD want to do. We've set ourselves strategic targets. We've developed concepts for lowering the cost, set the roadmaps, and we've basically built a program then from the bottoms up based on what we call technology synergy teams, made up of NASA Centers of Excellence, universities, industry, the DoD. We prioritized the technology and built the program from the bottom up that's we think is balanced and consistent with the budget that we think we need to do that. This is what the challenge looks like. The challenge has been stated as part of what the administrator calls the 3 pillars for success within the aeronautics and space transportation technology enterprise. And those challenges are this. We basically believe to open up these opportunities in space, cost of pound payload to Earth orbit has to be around $1,000 per pound. That's approximately an order of magnitude lower than it is today. Shuttle costs are slightly under $10,000 per pound. RLB program, in which X-33 is the demonstrator of that capability, we believe will go some to bring that cost down by that order of magnitude. We believe that if we really want to explore the outer solar system, interstellar space, we believe the future really has got to get payloads to hundreds of dollars per pound to be able to do that. And that's another order of magnitude out of space launch costs. So those are basically our guiding challenges within this time frame. Within the next 10 years, an order of magnitude in cost. Within the next 10 years, another order of magnitude in cost. And that's the top-down strategy that we've used to lay out our technology roadmaps. Transportation can be segmented up like this. We do a lot of things in low Earth orbit. In fact, almost everything we've been doing in the last few years has been low Earth orbit. There's a lot of things we can do to lower the cost of the operations in low Earth orbit. There is the capability required to put things from the ground into low Earth orbit. And those come in all kinds of sizes, from very small science payloads down to around 200 pounds. To very large payloads. Some of the communication satellite requirements require very large payloads, and a lot of those large payloads are going to geosynchronous orbits. They require a transportation system to get them there. And of course, exploration is a completely different set of requirements within itself. So we parceled the segments up like that, and we basically laid out a roadmap that looks something like this. Now, we put some pretty pictures on this roadmap to represent some of the concepts that we were looking at that we think will be available in the future to lower the cost of space travel. We're maintaining a base research line which is looking at 25 years. We're also looking at space transfer technology. That is, how do you get payloads from low Earth orbit to higher Earth orbits, or transfer payloads to the lunar surface or Mars. We're looking at advanced reusable technology. These are things downstream of the current RLB plan, which is really driving to getting access to space down to costs that are consistent with today's airline operations. Highly reusable systems. And then we're looking at low-cost boost systems. Now, we've looked at ways to get the cost down to space launch. Today, the systems are very complex. We think we've got to drastically simplify the systems to bring down the cost. And that's a lot of what this part of the program is doing. Another way to get costs down is quit throwing things away. Use them over and over, and get high reusability out of them like today's airlines. RLB, the X-33 program, is starting to look at that. We're looking at ways to get launch vehicles to be able to reuse as much as 200 missions. Weight is a big cost when you're trying to take that weight and overcome the gravity it takes to get to low Earth orbit. About 70% of the weight of the payload is a transportation system that has to take it to its final destination. So if we drop the weight of the transportation system, you lower the cost of space launch. And so much of our technology is tied up into reduction in weight, simplification, and long life. But in the future, we're going to have to get away from chemical propulsion systems. We're going to have to find new energy sources. So a lot of what's in the research line is looking at new energy sources. Way to utilize the solar energy to power spacecraft. Fusion energy, for example. I talked about small payloads. You may wonder why we're looking at technology to get small payloads up. This is the history of the small sat market. And you can see it's been a very active market. This is the size of those payloads. And you can see about 75 or 80% of those payloads are within 150 kilograms. Very small payloads in which we get a lot of technology and science out of. Let's see, this is the weights here. This is what we believe the future looks like from a small payload point of view. Again, around 150 kilograms, you can capture 80% of those payloads. These are payloads that are just sitting there waiting to be built. These are things that university commercial partnerships have generated as important things to do if we're going to commercialize space. There's 49 payloads sitting out there waiting to be built. We can capture almost all of them within the 150 kilogram payload size. And this is the kind of things that they're trying to do. You can just read down the list of the technologies that industry thinks is important if we're going to commercialize space. And again, this is a program that generates partnerships between the university, the education community, and the commercial community that allows industry to work with the universities to build payloads which demonstrate technology which will be usable for the industry in the future. Very important to NASA that we do that. The Low-Cost Boost Technology Project with the Advanced Space Transportation Program, first objective is to enable a small launcher that will carry those payloads. Now, we have launchers that can carry the payloads today, but not at a cost. These are very low-cost technology projects and science projects. The launch costs sometimes 10 times more than the satellite itself. So we need a very low-cost launch capability to put those payloads up. We're targeting 150 kilograms, and we're targeting $1.5 million per launch, which is a significant, that's a factor of at least 7 below what we can put those payloads up today. And we're targeting that for 2001. So this is a relatively near-term technology. What has generated the capability to do this is simplification, simplifying aerospace systems to the point where it's no longer, you don't any longer have the very unique specialized parts that we have in aerospace today. We're looking at common manufacturing techniques, parts that you can take off the assembly line in many manufacturing facilities in the United States today and build a launch vehicle out of it. The fast track engine, we call it fast track, is an example of that simplifying process. This is an engine that we project is going to be a factor of 10 lower than any engine its size that you can buy on the market today that's currently being built. It will fly first. It will power the X-34 in early '99. It was the primary propulsion system for the X-34 flight demonstrator. And what we're calling the Bantam flight demonstration will take place in late '99. At this point, NASA's out of it. Again, going back to the job of NASA, our job is technology, and we've taken this technology up to the point where we've demonstrated in flight, which we believe you've got to do in this situation, because a lot of the cost is tied up in launch operations. Unless you go prove that you can cheaply launch something, you really haven't done anything. You've generated some nice technology. Well, we believe that we've got to go prove that. And once we've done that, the industry is in the lead. What's going to drive this launch vehicle is the commercial and the science market that's going to fly on the launch vehicle and this company being able to say, there's not a risk anymore because we've matured the technology to the point where I can get venture capital to allow me to go develop this launch vehicle. We're depending heavily on a study we call the Highly Reusable Space Transportation Study, or HRST. It's looking at very advanced approaches to space launch, targeting about $400 per pound. We believe that around, or $100 or $200 per pound. We believe that around $400 per pound, according to the Civil Space Transportation Study, that the market will expand dramatically. We get into cost where space becomes a commercially viable market, and even viable for individuals to go to space. You've heard Buzz Aldrin maybe talk about space tourism. It's a real thing if we can get prices down around $100, $200 per pound to low Earth orbit. There's a lot of concepts that we're looking at. We're looking at combination propulsion systems that have systems on it that breathe air, part rockets, part air breathing, combined cycle systems. A lot of the technology, we believe, is at the lower level but has the greatest potential to enable this kind of system is in the combined cycle propulsion area, where we have an integrated air-breathing rocket system, a system which has the capability of being an air breather like an airplane up to about Mach 8, and at that point the rocket will take it onto orbit. Again, weight in the launch vehicle is important. Most of the weight of the space shuttle is in the liquid oxygen. If you don't have to carry all that liquid oxygen, you don't have to carry that weight and that amount of structure with you to orbit. And so if I can breathe atmospheric oxygen on the way up, it's liquid oxygen that I don't have to take on the launch vehicle. Of course, this study is looking at other things like launch assist. Again, it's even better not to carry, if I can carry less oxygen. If I don't have to carry that energy at all, it's even better. Just leave the energy on the ground and throw the launch vehicle up to an altitude which overcomes that initial phase of the launch. So we're looking at things like magnetic levitation, which will throw the launch vehicle to an altitude, and then the onboard systems take over. The current program is laid out like this, and again, like the other project, we start with component technologies, go to system technologies. In this case, combined cycle propulsion, we believe, is a system technology that has great promise in the future. And then once you've matured the program, the technology to the point where you're ready for a flight demonstration, and we'll go do that. Again, at this point, NASA's done its job. Once we've retired the rest, we expect the industry to take this to the next step in the next generation launch vehicle. Our goal is $100 per pound, and this is launch technology beyond the X-33 program, which will fly to 1999. The X-33 and the RLD is currently an all-rocket propulsion system. It's a propulsion system very similar to the space shuttle. It looks a lot different, but its performance is not very different than the space shuttle systems. We've got to get a drastic increase in propulsion system performance before we can increase the life dramatically of a space transportation system. And that's one thing that we're looking at is a performance increase of the propulsion system. And we believe you can do that with a combined cycle air-breathing rocket propulsion system. The other thing is increased life, stronger materials, lighter weight materials, and that technology is booming. The advanced energy sources, some of those concepts are coming out of the HRST studies as well. And so within our space transportation research area, we're doing research in mag lifters, advanced cycles like magnetohydrodynamics, which actually utilizes the surrounding air as a propulsion system. And the way this system works is we've got a small rocket motor here which generates electricity, an electric current, and a magnetic field which ionizes the air and accelerates it around the vehicle and lifts the vehicle into space. This technology has applications both in launch vehicles and in space transfer systems as well. And then again, advanced energy sources like fusion. We get criticized sometimes for working on fusion concepts because the Department of Energy has spent billions on looking at fusion energy, and frankly are not close to generating power with it. But what they have done is, in some tests, the fusion has maintained itself. And since we're not trying to generate power with a fusion power plant, all we need to do is have the system maintain itself. So the work that the DOE has done up to now is essentially given us a propulsion concept which utilizes fusion energy, because if the fusion can maintain itself, we've got a propulsion system. Now there's a lot of other propulsion technology that's got to be wrapped around that system to make it a viable system. The technology readiness for that is at a very low level, and I wouldn't expect that to be available until 2020 or so. There is another critical study going on that we call the Advanced In-Space Transportation Study, or AIST, and it is looking at reducing the cost of getting payloads from low Earth orbit to high Earth orbit. Today's current costs are around $18,000 per pound from low Earth orbit to high Earth orbit. We're trying to reduce that by an order of magnitude. We think in the near term it could go to $6,000 per pound, and we're striving for $1,000 per pound to, say, a geosynchronous orbit for a commercial satellite. Some of the near-term technologies that look like they are viable solutions is the solar thermal propulsion system, for example, that utilizes the solar energy to heat a working fluid like hydrogen and expel it in a propulsion system. Nuclear fission, tether systems. We're looking at tether systems, and they have not only the capability of raising the orbit of the satellite, but deorbiting the satellite. I'm sure you've been reading about the amount of space debris we have in orbit. In fact, we've got to do something about getting rid of a lot of that space debris in the space station orbit. This has the capability in the future to apply a very simple passive tether system on the satellites in the future. And when the satellite dies, you reel the tether system out and deorbit it. You don't leave it in space. So there's a lot of potential there. This is some of the technology that we're working on within the space transfer technology area, again starting at the components. And if you look at just the solar thermal stage, the technology is really in the high temperature engine. This engine would like to run about 5,000 degrees Fahrenheit. We're within that capability today. Again, materials technology has boomed with the new ceramic materials. We intend to fly a small solar thermal stage on shuttle in 1999 to demonstrate this concept. We call this Shooting Star. It will have a rhenium engine on it. The next generation engine may be something like hafnium carbide, one of the new ceramic materials. The other technology is in the lightweight solar concentrators, inflatable structures. This structure is made out of 3 mil Kapton material, which is packaged, all folded up into a nice neat little box. It weighs essentially nothing. When it goes to space, we inflate it. It rigidizes in space. You have a thin film Fresnel lens made out of the same material that focuses the solar energy on the engine. Solar electric is going to be essential to going to Mars, we believe, or doing any other exploration, including the robotic exploration we're doing. The New Millennium Program, Deep Space One mission will fly next year. It will be powered by the first solar electric ion propulsion system. as part of the NSTAR program, and Advanced Space Transportation is funding part of that. And then we're planning a tethered propulsion system experiment in 1999, which will fly on a delta stage and actually deorbit the stage for the delta. I'm going to quickly run through this. I'm going to basically tell you now that we always get smarter as we go through these planning processes. I'm not going to stand here and tell you any of the concepts that I've shown you today are the right answer. It's concepts that have high potential and deserve our attention as far as working in the technology program. But there's other concepts and other technologies out there that are also maturing. One thing that has happened over the last year is the real desire to go to Mars. And so the technology program of the future, the next year's technology program will start to build up that technology capability to make a Mars mission and reduce the cost. And the administrator has set a goal of a $25 billion program to go to Mars, and that's a factor of 20 lower than our initial cost estimate in 92. Our recognition that if we're going to continue to fly a space shuttle, you can't continue to fly a space shuttle in its current configuration. And if it flies, even if we have a new reusable launch vehicle, the shuttle's going to be vital for several years in the future, so we're going to need to upgrade it. RLV, if it becomes a operational vehicle, we'll need an upper stage. We're looking at reusable upper stage capability that would support RLV. The shuttle upgrade program is laid out like this. Where in phase 3 we start to make major upgrades in the shuttle propulsion system, going away from the toxic propellants that are on the orbiter today to safe propellants like things like LOX ethanol, LOX methane, which are much safer than the propellants we have on today. And then phase 4 starts to look at a liquid flyback booster to replace the solid boosters on the space shuttle. We're already looking at that technology today. Of course, as a spacefaring nation, this is our prime objective. And the technology required to go to Mars is vast. About 70% of the cost of going to Mars is in the transportation system. About 40% of that is just getting to low Earth orbit. The other 30% of it is getting us from low Earth orbit to Mars and back. These are the transportation systems that has to become viable before we can go to Mars. A significant technology is going to be aero capture. It looks like the way to get significant weight out of the program. So I expect the technology work in aero capture to be increased. Solar thermal is a possibility for not only transportation systems, but you heard Mrs. Johnson Freeze talk about power, or somebody in the meeting plenary this morning talked about the need for power. Some of the technology that we're working on in the solar thermal stage, like the expandable, the inflatable structures, the lightweight concentrators, are directly applicable to space power systems. They could be beamed back to Earth, space power systems that could be put into Mars orbit and generate power that would allow us to get away from a possibility of having to use a nuclear system, because that looks like a prime way to generate power right now. And of course the commercial needs. Fast ways to get package deliveries from one side of the earth to the other. FedEx and the Red Cross are interested in doing that. And we believe in the relatively near term, if we can get the cost of throwing these kinds of payloads on the other side of the earth within $200-300, that's a viable thing. It changed the way we do business today. Our peer review looks like this, and this is my last chart, so I'll stop here. I'm not making the decisions on what we continue to do. The technology community of this country is making the decisions on what technology needs to be done. We've partnered with every technologist out there, we believe, and we think we've got the smartest program we can put together. And it's going to require also a high-level peer review to make sure that we stay viable and focused on our goals. And with that, I think we may have a minute for questions. Yes.
You talked about getting away from plastics and fuels, but it's assuming that you're pushing the solids right through the shuttle.
It's not only the solids, but it's the onboard components that implement.
Are you going to implement some sort of a hybrid small-scale demonstration program?
Well, we already have a hybrid demonstration program going on. We're getting ready to fire a 24-inch motor. A small company has launched several hybrid sounding rockets from Wallace recently, so it's a viable alternative.
You've covered a lot of ground very quickly, but I think one of the very last things you put up just shocking me, and I think in some ways represents a lot of what I've seen. There's a whole lot of a miracle happens here in some of the things that you've written. $300 a pound for FedEx and the American Red Cross is something you're looking at as being a viable alternative and what society industry wants. Where did that magic number come from of people are willing to pay it?
There was a study done.
A study.
Yeah. And there's been several. One of the studies was the Civil Space Technology study. That was a group of industry and commercial users which looked at what is the elasticity of the market. What could happen if prices got to certain levels? And so they would envision at a given cost what could be enabled by that cost. There are things that can be enabled at $5,000 per pound. There's things that can be enabled at $1,000 per pound and at $300,000. Now, at $300 per pound, people start dreaming a little bit. Okay, it's hard to really say that the market will happen if you got to those prices, because you've got to believe at that point that if you build it, they will come.
But it seems that all of this is based on if you build it, it will come. That a whole lot of what you've been talking about is based on a study or that this will happen.
Some of it is, yeah. And what you basically have to do is work the technologies and test them. You have to test the market and see if it's really there. One thing we're doing is in the near future, or near term, is looking at the small payload market as a test market. We can do it at relatively low cost. We think we can do it relatively near term. And we're getting our feet wet a little bit at a time. And in the small market area, we're going to test the elasticity of that market if we get that going. That may start to prove a lot of these assumptions that's been made.
What will happen if it disproves it?
Then it's not the right thing to do. You do something else.
I believe the gentleman in the red shirt in the front row is next.
Yeah, you have any plans or desire to launch a solar sail in the next decade or so? Look at that as a test bed?
Yeah, JPL is, for example, leading an effort looking at solar cells. It's a viable solution to, it's slow, but for carrying cargo, heavy cargo, if you don't care how long it takes you to get there, it's a good solution. And part of the Mars architectures are split missions, where you take the cargo on a sort of boat like a solar cell or a solar electric system, and you send the humans later to rendezvous either in high Earth orbit or in Mars orbit. So yeah, it's a possibility, and that has been looked at.
For your combined cycle propulsion, are you looking to use any of the Lyles technology, especially for the aircraft things?
Well, Lyles looks looks like a viable technology. We're doing concept analysis and technology in parallel, and we're really driving at the low-cost solution. Lay systems are relatively complex. When you go to higher and higher Mach numbers, the system becomes more and more complex because you get into moving structures and things like that. I believe somewhere between where we are today with an all-rocket and where NASA was going, for example, could be a low-cost solution, a bucket in the curve, which says that we can meet our low-cost goals here. I would like to go to orbit at Mach 8 or Mach 10, not Mach 25. Yes.
I noticed on some of your advanced concepts, when you were talking about the exotic stuff, you had something called anti-gravity. That sounds like the favorite propulsion system of E.T. and the invaders on Independence Day.
I forgot to put warp drive on that.
I did read that one slide correctly, didn't I?
Anti-gravity is a misnomer, and there's a lady here, Dr. Ning Lee, who will speak about that part of the project, I think this afternoon. It's really a gravity modification experiment, and I hope you can attend that because it requires a lot better discussion and deserves a lot more than I can give it. But it is a gravity modification experiment that we're investing in.
Yes. Considering the fact that there are, at last count, about a half a dozen different methods of shooting material off the surface of the Earth into space using various kinds of mass drivers, these methods have been tested and shown to have very high accelerations, very low cost, not for putting people or high-value cargo, but consumables and construction materials in space. I just wanted to challenge you and say, why haven't these methods been worked into NASA's plans? Why is NASA pretty much ignoring mass drivers?
Well, I don't think we're ignoring them. There's a lot of concepts out there that
Some of these are quite well proven.
Yeah. The acceleration is high, and you have to look at that. It's not that we've discarded them. What we have to do in building the program is that we try to balance the program as well as we can with the resources we've got. Those concepts are constantly being worked at. If you remember, one of my first charts was this cycle that says, out of the concepts we generate technologies. Now the technologies, we go back and look at the concepts again and see, what have we really enabled? Have we enabled that concept, and now does it become a higher priority than the others? And that cycle is always continuing with new advanced concepts being filtered in all the time. So we're constantly going through that relook at concepts, and we don't discard anything unless it's proven. I don't know of anybody that's proven it that won't work.
Well, first of all, there's several mass driver concepts have been demonstrated in the laboratory and in field tests to achieve reliable high G accelerations and can cheaply put things into orbit. But there's a synergy here. If the problem with single stage to orbit is the technical risk, are you going to have any payload margin? You can remove this technological risk if you have a mass driver that can put fuel into orbit. You just have enough fuel on the single stage to orbit vehicle to get you into orbit and to rendezvous with a fuel tank. This incredibly lowers the technological risk of single stage to orbit. And I would suggest that NASA ought to really look into that synergy.
There's a version of that that's actually very simple. It's called an air scoop. The original concept back in the late 50s was called the ProFAC, Propulsion Fluid Accumulator. And he's correct, it's probably the simplest way to make single stage orbit real.
Okay, thanks.
So one of the things I've been looking at, you're going up to payloads of about 20 tons in your projected vehicles. And if you're going to do several things, like send a modular portions of power satellites, if you're going to launch a good number of large payloads to Mars to build up for Mars space, and if you're going to build a second generation space station without the terrible difficulties we're having now with the tiny modules we're building for the first one. You're going to have a vehicle that at low cost, they can put up modules in the size of 50 to 100 tons, so you don't have to do all this detail work in space. You do that detail work on the ground, you put up a bigger module. So I'm interested in seeing what you're looking at in terms of those larger payload sizes, which will, if the market becomes viable, which will be determined by the launch technology, of course, require a good large number of launches from such a vehicle.
No, you're exactly right. In fact, the transportation systems that are really lacking are really on the very small end of the scale and the very large end of the scale. The architecture studies for Mars right now looks like we need at least 80 metric tons in the lower orbit to get the Mars architecture up. So we are looking as part of the Mars study as at a large booster to do that. We're also looking at other needs around the country that also requires the heavy payload. And so we're looking at it. I'll be glad to show you the kinds of vehicles. Yes.
This is the last question, by the way, sir.
Yes, one of your things, you had something called pulse detonation wave propulsion or whatever. What is that anyway? Is that like the old pulse jet of the V1 buzz bomb?
Something like the buzz bomb. It basically, that concept uses the pressure of the detonation to expel or to create thrust. And it happens in a pulse, which means that and the good thing about that concept, by the way, is you don't have to pump the propellant up to the operating pressure of the vehicle. You can actually inject the propellant when the system is at low pressure. It detonates and goes to high pressure when the propellant system is shut off and creates thrust. Now, to get a steady thrust, of course, you've got to generate a steady pulse of approximately 100 hertz or so. And so we're working on systems which inject the fluid at low pressure. It creates a detonation pulse on about 100 cycles per second frequency and generates thrust that way. It's a very simple system too, by the way. It's basically a tube with a low pressure injector on the end. And
would it be more of an air breather or a rocket?
It
The
can
buzz
be-
bomb was an air breather.
yeah, it can be any one.
Yeah, but now the buzz bomb also the Germans had to use a catapult to launch it. So if this was an air breathing system that you're talking about, wouldn't you have to use something like a catapult or another aircraft or something?
Yeah, if it's an air breathing system, and of course there's combined cycle options for the pulse detonation wave, which you could run on onboard propellants or onboard locks initially and convert over to an air breather. But you know, the real technology is what's the thrust of the weight of these things. Can you build this system light enough weight that it can get off the ground, and can you maintain a 100 hertz frequency pulse like that? But if you can do those things, it looks like the performance increase is 10% or so above the day. The real advantage is the low pressure fuel injection, which gets me away from the high pressure pumps or high pressure pressurization systems to inject the fuel.
Thank you very much, Mr. Lyles.